Name of subject internal combustion engine. Name of chapter SI engines fuel supply system. Ignition system combustion. Name of topic derivation of simple carburetor by neglecting the effect of compressibility of air. Contents derivations of simple carburetor by neglecting the effect of compressibility of air. Dear friends, today we are going to discuss on very important point in the carburetor, and that is nothing but the derivation point. The derivation of simple carburetor by neglecting the effect of compressibility of air is one of the derivation which is one of the basis to solve the different numericals which will come on the carburetor. So we can decide the dimensions of carburetor with the help of this derivation. So in the case of carburetor, we have to see the two different types of derivations. One derivation is this one, that is a derivation of simple carburetor by neglecting the effect of compressibility of air, and the another derivation which we have to see after this one, and that is nothing but the same derivation, that is derivation of simple carburetor by, instead of neglecting, in that case we have to consider, or by taking the effect of compressibility of air. So these two derivations are very essential in the study of carburetor. So today we are going to discuss the first derivation, that is the by neglecting the effect of compressibility of air. So to understand thoroughly this particular derivation, we'll proceed to see the notes, and with the help of the notes we can understand this derivation. So again, we can say the expression of air-fuel ratio for simple carburetor by neglecting the effect of compressibility of air. Okay, so to understand this particular concept or two derivations, we must have to understand again the diagram of simple carburetor. So this diagram is a part of this particular derivation. As we already discussed the working and constructional features of simple carburetor, the same kind of a diagram is present over here also. Again, as we know, this is the venturi which present inside the carburetor body. Here is the venturi and this is the venturi throat. So at the throat section of the venturi, there is one fuel jet which is connected to the float chamber with the help of one tube connection. Okay, so the float chamber is again connected to the fuel tank, means from the fuel tank the fuel will come inside the float chamber, and from the float chamber that fuel will insert in the throat section through the fuel jet which is present over here. Okay, please concentrate on the mouse indicator. Again, as we already discussed, to avoid the spilling effect of petrol, we always have to keep this particular jet, nozzle jet, above Z meter or Z distance than this particular float chamber. So always, my dear friends, remember there should be a some difference in the height of fuel jet and the level of the petrol inside the float chamber, that is a H or Z, whatever indications we are using. Here we are using Z distance which is above than that particular amount of petrol inside the float chamber of this tip of the nozzle, we can say. So again, here we have a throttle wall. Through the throttle wall, the amount of air fuel mixture will supply to the engine cylinder, and this side is the entry section through which the amount of atmospheric air will insert in the carburetor body, and here is that particular choke wall. So in this case, here we have to consider few things to understand this derivation. So what is our consideration? Let us consider section 1 1. Suppose here is 1 and here is 1, and this is that particular section. Section 1 1 is the entrance section through which the amount of air will come inside the carburetor. And let us consider section 2 2. Here is 2 and here is 2. Section 2 2 is a throat section of the venturi. So we have considered section 1 1 is a entry section through which the amount of air can enter inside the carburetor, and section 2 2 is the throat section of the venturi. So along with these two considerations, we'll proceed to understand the things. So whatever we just considered, it is written over here. It is a part of derivation. Whenever the derivation will ask in your examination, that time you start with this diagram. You have to explain this diagram thoroughly, and whatever consideration is required, you have to write in the part of derivation, like this one. Okay, so in this case, as we already discussed, Z is the difference between the height of nozzle tip and the level of fuel in the float chamber to prevent the spilling of petrol when vehicle is stationary. As we discussed earlier about this, here the throat of the carburetor, that is neglecting the compressibility of air. So we are looking to understand the derivation where the neglecting the compressibility of air. So what do you mean by the neglecting the compressibility of air? So again, with the help of this diagram, we understand this concept. So suppose the amount of atmospheric air enters inside the carburetor body from section 1.1. As it enters in the section 2.2, where is the throat of the venturi is present, as it enters in the throat section of the venturi, as we already discussed, the pressure of air goes down, and as the pressure decreases, velocity increases. Okay, so the throat is nothing but decreasing in the cross section. So as we already discussed, this cross section is different one, and this cross section is totally different one. So as air comes inside the throat section of venturi, definitely there will be some compression of air. Its pressure will goes down and its velocity will going to increase. So during this derivation, here we are going to neglect the effect of compressibility of air. So we are not going to consider, as air enters inside the throat section of the venturi, we are not going to consider its effect. Okay, so it's not our task in this derivation to consider the effect of compressibility of air. So as the air will get compressed, whatever effect will happen, we are not going to consider during this particular derivation. So that's why the name of this derivation is what? Neglecting the effect of compressibility of air. So we are totally neglect the effect of compressibility of air. So the things are written over here also. Here the throat of the carburetor, that is neglecting the compressibility of air, assuming. That's why if we are going to assume, or if we are going to neglect the compressibility of air, then we have to assume the initial velocity of air to be 0, and let us consider C1 is the initial velocity of air, that is equal to 0, density of air to be constant, and considering section 1.1 at entrance and section 2.2 at the throat section, and then we are going to apply the Bernoullis theorem. So what we have considered, the initial velocity. See, when air enters inside the carburetor body, it has some initial pressure, it has some initial velocity. So because of the neglecting the effect of compressibility of air, we have considered the initial velocity. Let us consider initial velocity is C1 of the air, that is to be 0. That's why we have considered C1 is 0 and density of air is to be constant, and considering section 1.1 at entrance and section 2.2 at a throat section. And now we are going to apply the Bernoullis theorem or Bernoullis equation. I think all of you are knowing about the Bernoullis theorem. So though we know about that, here I have written that theorem. So we know the Bernoullis equation is what? P1 by rho g plus C1 square by 2g plus zg, and is equal to P2 by rho g plus C2 square by 2g plus zg. So why we have written over here the left side is P1 and right side is of P2? Because we are going to apply the Bernoullis equation or Bernoullis theorem to section 1.1 at the entrance section and section 2.2 for the throat section itself. So now we are only talking about the air. Okay, there is no question of fuel right now. Only we are talking as the atmospheric air enters inside the carburetor body, and it's and we are assuming its effect of compressibility we are neglecting. Okay, so we are applying the Bernoullis equation to section 1.1 and section 2.2. Only we are considering air right now. So there is no question of fuel right now in this particular equation. So, as we know, we are going to apply the Bernoullis equation for section 1 entrance and section 2 that is the throat section. We know the standard equation of Bernoullis equation, that is P1 by rho g plus C1 square by 2g plus zg, and for similarly for section 2 the equation is P2 by rho g plus C2 square by 2g plus zg. So we know P is nothing but pressure, rho is nothing but density, g is nothing but gravitational acceleration force, and here we have considered the initial velocity of air is c1, and here we have considered the velocity of air at the throat section is the c2, and similarly pressure of air at the throat section is p2. So z is nothing but the height which we represented in the diagram, and g is again gravitational acceleration force. So this is the general Bernoullis equation. So now in this case, what we have considered, the value of initial velocity, that is c1 is equal to 0. That's why if the c1 is 0, then this term becomes 0, as well as if the z is not applicable for section 1. So in this case, there is no use of this particular height, because this height is applicable at section 2, and this is majorly for the fuel, and we are writing the equations for air. So there is no need to write the z in the part of equation over here. That's why here these two terms may neglect, or this will be 0 and this will be term directly we are neglecting, because there is no need to consider the z for section 1. So what is remaining? Only remaining is this equation, that is P1 by rho g for section 1. And similarly, what about the equation of section 2? The same equation we have written over here, that is P2 by rho g plus C2 square by 2g plus this zg as it is. Okay, so again when we proceed for the further simplification, in this case P1 and P2, as we already discussed, whatever things we considered, P1 and P2 are the pressure at section 1 and section 2 respectively, and C2 is the velocity at section 2 in meter per second. So velocity unit is meter per second, and generally we can consider pressure in Newton per meter square or bar itself. Okay, so density rho, it stands for density. So generally we are talking about the air part itself. That's why you have to consider rho for air. That's why we can write rho suffix small a, that is nothing but density of air in kg per meter cube. So these all are our considerations. So along with this consideration, we are going to rewrite this equation. Okay, so how we can rewrite this equation? So we are just rewriting this particular equation again. So this is again very important to rewrite the equation. Suppose we are going to rewrite this equation. So the g is there, so 1 by g, here also 1 by g is a common, so this g and this 1 by g will get cancelled to each other. So what is remaining in this case? We already written the equation like this: P1 by rho a plus P2 by P1 by rho a is equal to P2 by rho a plus C2 square by 2 plus this ZG as it is. Okay, this ZG which is present over here, this ZG we are written as it is. So this all Z, this gravitational force will get cancelled to each other. That's why I'm not written over here. So the further simplification is again possible. So we can write, we can further simplify the equation. This P1 by rho a is equal to this P2 by rho a is equal to C2 square by 2. Again, there is no question of this height. So we can directly neglect this particular ZZ, as we discussed in this case. When we are writing for the air, there is no need to consider the Z. When we have to consider the Z, when we are talking about the fuel, when the fuel enters inside the fuel jet because of this pressure difference, that time we have to consider Z. For writing the equations for air, there is no question of this particular Z. That's why we can directly neglect this particular Z into G equation. So we can rewrite the equation again. The simplified equation is what? P1 by rho a is equal to P2 by rho a is equal to C2 square by 2. Again, further simplification is again possible. So we just keep C2 square at one side, and P1 by rho A and P2 by rho A we can take at one side. So this 2 is again there, and this will be further simplified equation, because rho A, that is density of air, is the same base we can write, and this 2 will come at this side. So this is at denominator, so we can write at the numerator. So this P1 by rho A is positive, and when it comes, this P2 will come at this side. That time that is P2 will be get minus. So we can simplify the equation, and that becomes C2 square is equal to 2 into P1 minus P2 divided by rho A. So this is the simplified equation. Again, here is the C2 square, so we can again simplify the equation. So under root of 2 into P1 minus P2 divided by density of air. This is the simplified further equation. So similarly, the next equation is what? We know what is the mass of air per second. So generally we have the formula of mass of air. How we can calculate the mass of air? With the help of this formula: area into velocity into density. So A stands for area, C stands for velocity, and this rho stands for density. So if you want to calculate the mass of air, we have this general formula to calculate the mass of air. So when we talk about the mass of air for section 2, then how we can write the equation? Mass of air at section 2, that is equal to A2 into C2 into density of air. So that A2 C2 stands for the area of the throat section, and C2 stands for the velocity of the air at the throat section. So this is again very important. So again, the further simplifications, we have the CT equation. So we have already calculated the value of C2 in earlier derivation part. So directly we can take the value of C2 from here, and we can put that value in the equation of this one. So put the value of C2 and rewrite the equation, and finally we will get the equation like A2 into under root of 2 P1 minus P2 by density of air into density of air, as it is. These two terms we have written over as it is. So similarly, after further simplifications, what we can write, the density of air, this density of air and density of air will get cancelled, and what is remaining, that is this density of air will when we will multiply this density of air to this particular bracket of under root, that rho A square will be there, then this rho A square and this one rho A will get cancelled. So what is remaining? A2 into under root of 2 rho A into P1 minus P2 give equation number 1. So this is our equation number 1. So as we already discussed, A2 is the area of venturi throat, and its unit is in meter square. Okay, so up to equation number 1, our calculations are based on the air basis. Okay, section 1 and section 2 where the entrance of air, and section 2 at the throat section, and accordingly that we have considered the equations for air, and we have got the equation for mass of air. So with the help of that particular AL calculations, we have the mass of air and equation number 1 like this. Now we are going to calculate for the flow of fuel, and now we are going to consider the equations for fuel calculations, or the fuel equations we are going to calculate now. So similarly, now we are going to consider section 1 that is the initial section, and section 2 that is the throat section. Now similarly, by applying the Bernoullis equation, as we already neglecting the compressibility of air, so that two terms, that C1 square by 2g plus zg, that will be get cancelled. Okay, because we are not considering that C1 is equal to 0. Again, that's why this left term, that is P1 by rho f. Now if you consider, or if you see this term here, we are writing rho f because we are writing for flow of fuel now. Okay, so earlier we have considered the air, density of air. Now we are going to consider density of fuel. So rewrite the equation for density of fuel. So P1 by rho f is equal to P2 by rho f plus C suffix f. Now we are going to consider C suffix f is the velocity of fuel at the throat section. Earlier we considered C2 is the velocity of air at the throat section, but here we are considering CF, that is C suffix F is the velocity of fuel at the throat section, that is CF square by this particular 2 plus Z into G. So again we have this particular equation. So I have written over here CF is the velocity of flow of fuel and G is the gravitational force. So rewrite the equation once again. So we can write the equation we can write the equation this CF. If you calculate the CF equation, then we can simplify this P1 by rho F and then take down this P2 at this side, and this rho F base is constant. Here Zj is plus. When it comes to this side, then it will be minus term, so Z into G, and again CF square, so we can directly write under root to calculate the CF. So we have the further equation, that is under root of P1 minus P2 by rho F minus ZG, and complete equation bracket square. So again the further simplification, sorry, it's not the bracket square, it is multiplied by 2, because here is that particular term 2 which is present at the denominator side, and when it comes to this side, then it will be multiplied. So we have the equation finally, and give equation number 1 for C suffix F. So this is the equation of velocity of fuel at the throat section. So as I told you earlier, here we have to consider Z, because if you see in this particular diagram, as the carburetor depression takes place. Okay, suppose this is the fuel tip or fuel nozzle which is present over here. So as the pressure difference creates, so high pressure fuel will come up at the low pressurized, and there is a gap of Z. Okay, that's why for the fuel flow we have to consider this particular Z. For the air, we have not considered this Z, and that's why we have also not considered that gravitational force. So here you have to consider the Z also, as well as the gravitational acceleration force G also. So we have the equation number 2 for the velocity of fuel at the throat section. So what we have calculated till mass of air, this gives equation number 1, and this is the second equation, that is nothing but the velocity of fuel at the throat section, that is CF. This is equation number 2. So here I have written the Z means the petrol surface being lower than top of Z by Z meters. So the pressure difference becomes P1 minus P2 minus ZG into rho F instead of P1 minus P2. So what is this? This and this one is what? If you see in this equation, the pressure difference is P1 minus P2 into ZG. If you take this rho F over here, that is nothing but rho F, and instead of P1 minus P2, where is P1 minus P2? In this equation here we got P1 minus P2. So for the mass of air only we got P1 minus P2, but when we consider the flow of fuel, that time we are getting the equation like this. This is P1 minus P2 minus ZG into rho F, like this one. So this is the basic difference between the equation of air and equation of fuel. So similarly, as we already calculated the equation of mass of air, so if we want to calculate the equation of mass of fuel, similarly we can calculate, we have the equation area into velocity into density. So here we are calculating for fuels, that's why we have to write area of fuel AF at the throat section, CF, that is the velocity of fuel at the throat section, and rho F is nothing but the density of fuel. So we have already calculated the value of CF over here. So CF value, we have put this value in this equation and rewrite the equation, and the equation become mass of fuel is equal to AF into under root of the full term 2 in bracket P1 minus P2 by rho F minus ZG bracket close, and the term is multiplied by density of fuel, that is rho F. So these two terms written as it is. So again the further simplification, this rho F is outside the under root sign. When it comes inside the under root, then rho F square will be there, and so we have have the next further simplified equation, and finally this one rho f and this one rho f will get cancelled to each other, and we have written over here p1 minus p2 minus zg rho f into rho f. So as we already discussed, this is already written over here. So this is the difference here we got in the case of air, that is p1 minus p2, and in the case of fuel we got p1 minus p2 minus zg into rho f. So likewise the difference is present over here. So give equation number 3. So here we got equation number 3 for mass of fuel. So whatever equations we got, mass of air, then CF, and the mass of fuel. So till time we got the 3 equations for the neglecting the compressibility of air case. Similarly, if we want to calculate the AF means what? That fuel orifice area at the throat section. Okay, so AF is nothing but that particular area of the throat section fuel jet which we are going to calculate. So where AF is the cross sectional area of the fuel nozzle generally. Okay, so as we have considered in the case of fuel, the fuel jet which is present inside the throat section, and AF is the area of this orifice. So generally in numerical case we have to calculate the dimensions of the nozzle. That time we have to calculate these things. So similarly now with the help of this equation 1, 2, 3 we can calculate the AF also, and AF is the cross sectional area of the fuel nozzle in meter square. So if we want to write the equation in the form of mass of air to mass of fuel, because the air fuel ratio is always described in terms of mass of air to mass of fuel. So we have already calculated the equation of mass of air, which we have written over here, A2 under root of 2 rho A into P1 minus P2, and this is the equation of mass of fuel, that is AF under root of 2 P1 minus P2 minus ZG rho F multiplied by rho F itself. So again simplified the equation, this A2 by AF write separately, then rho A by rho F under root sign and write the equation separately, and the remaining equation under root of P1 minus P2 divided by P1 minus P2 minus Z0 F. So the same equation I have written over here in simplified manner, and give equation number 4. So this is again equation number 4 for this particular mass of air to the mass of fuel. So we can say this is the final equation. We are moving to see the final equation. Now by considering the coefficient of discharge of fuel and the coefficient of discharge of air into the account. So in this equation we have not considered the coefficient of discharge of air and the coefficient of discharge of fuel. So sometimes in the numericals they will give a given data about coefficient of discharge of air itself. So coefficient of discharge of air is indicate CDA, and coefficient of discharge of fuel indicate that is CDF. So coefficient is always multiplied to the term, so that's why we have written over here, and rewrite this equation once again. And if the value of z is equal to 0, so this z value becomes 0, this term this whole term becomes 0, and finally we can write the equation mass of air to mass of fuel is equal to CDA by CDF into A2 by AF into rho A by rho F under root of this particular term. So this is nothing but called as a final equation of neglecting the compressibility of air case. Hope you understood the derivation part of this neglecting the effect of compressibility of air. So thank you so much for watching this particular session. Thanks a lot.